Hello. So
Hello.
welcome everybody to this week's zkStudyClub. We have Bowe, who's going to talk about Halo and accumulation schemes.
Hi
Hi,
there.
Sean. You want to take it away?
Sure, yeah. Okay. So I'm Bowe. I'm a engineer researcher at the Electric Coin Company. I know many of the people that are in here. So it's nice to see you all again. Thanks for coming. So yeah, I'm an author of the Halo paper, along with Dara Hopwood and Jack Grigg, which are my coworkers at the Electric Coin Company. Halo is a new way of doing recursive proof composition. Our main objective was to avoid trusted setups, but there's a lot of other theoretical consequences of the ideas that we came up with. So this week I'm just going to be talking about Halo and this related concept called an accumulation scheme that came out in a paper that just like a month or two ago. Next week, Dara Hopwood will be talking about all the other things in Halo that are more practical and specific to the actual implementation stuff. So circuit optimizations and some clever math and some elliptic curve cycles and lots of really cool, fascinating stuff. So very excited to see that and hope to see some people at that as well.
Yep.
So
looking forward to it.
Yeah. Okay. So just as I'm not really sure what my audience was going to look like. So these slides are a little high level at times, and sometimes they're probably a little confusing. So I'll really enjoy feedback, and anyone's free to interrupt and ask a question. That'd be really great. I'd love to have conversations whenever there's issues or questions, and I could even probably just exit and modify the slides like as we're doing this if I see something pronounced. So just as a quick primer on recursive proof composition, notationally and conversationally, I'm going to talk about this in terms of the standard language. The prover knows a witness or claims to know a witness, and some instance such that if you run the witness in the instance of some arithmetic circuit, the circuit equals 1, or some system of constraints are satisfied, whatever it is that's encoding some computation. The prover demonstrates this by using some protocol that produces a proof, some non-interactive proof. And the verifier takes this proof and the public inputs, or the instance, and checks that the proof is valid. So there's so many different proving systems that have different trade-offs with each other. The one that's important for recursive proof composition is primarily, well, there's both proof size and there's also verification time. So
sorry to interrupt. I'm showing your video isn't on.
Right. I didn't want it to be on.
Oh, that's okay.
Okay, cool. All right, yeah. So the sort of snarks that are pairing based, that use trusted setups, have really good verification time. It's constant time, at least in the circuit size. And some of these other newer systems that don't have a trusted setup, like bulletproofs and the stuff that I'm going to talk about later with Halo, have linear verification time in the circuit size. But bulletproofs, for example, has logarithmic proof size, which is really useful and really awesome.
Can you clarify what circuit size means?
Sure. So circuit size, it depends on the proving system. It depends on the application, but generally it most often refers to how many multiplication gates you need, or in an arithmetic circuit that encodes your computation.
And for the purpose of this talk, will it always be multiplication gates?
I don't think I dive into what I kind of take for granted the size of the circuit, whatever that means. That it's I speak asymptotically throughout this entire thing, so I don't really dive into like a specific proving system. It varies. Like, for example, it's very difficult to compare Groth 16 with Sonic or Sonic with Planck because they have different arithmetizations.
The arithmetization used by Sonic and Plonk are covered in my talk. So
Cool. Yeah,
next week.
that'll be a useful thing to touch on. I kind of go over the abstracts and all the slides that follow. I don't think it's definitely just the asymptotics are the important part. Or if you want, you can just assume that the size of the circuit is the number of multiplication gates, because that's usually that's kind of that's the most fair comparison that I can think of that's applicable broadly. Okay, so recursive proof composition is when your circuit, within the circuit, it encodes the computations necessary to verify a proof using the same circuit. So inside of our circuit here, I've written verify as the verification routine, which takes some old proof, some previous proof, and some public inputs, which are actually a witness for the outer circuit. And it checks to see if the proof is correct, and then maybe it does some other computation step, whatever it is. And what this kind of instance of recursive proof composition is something called incrementally verifiable computation. Ooh, what happened to my screen? Do you all see black?
It's black.
Yeah, it disappeared out of nowhere.
Black.
Maybe you clicked V.
Yeah, you lost. You selected something else with your sharing.
I can't.
Stop sharing and try sharing again.
Try escape, maybe?
See, escape doesn't work. Oh, what's that?
Yeah, it should
It's a
work.
thing.
It should work. Yeah. Yeah, try sharing again. It should work now.
Alt F.
It's Wayland's fault.
You see your mouse.
I'm not using Wayland, but
Sean,
yeah.
do you want? I can boot you off sharing. Should I do it?
Yeah, can you do that?
Yeah, that might be why. Yeah.
So I have a question in the meantime.
Okay, that fixed it. Okay.
um,
That was weird.
For the circuits, at each step of the circuit in the recursion, does it imply that it's monotonically decreasing in the circuit size? Because it's like the next circuit must have been encoded in the previous one. So it's like they're kind of like a subset of information. Is that fair?
Oh, Sean, are you muted? No. Yeah, you're muted, Sean.
Sorry. Yes.
Yeah.
Sorry, I was a little distracted when you asked the question, but I think I get the gist of your question. So the circuit, you see how this routine, can you see my cursor, by the way?
Yes.
Cool. You see how this routine takes C? Maybe it shouldn't in this slide, because it raises your question, which is, isn't this circuit bigger than this circuit because this circuit encodes the description of it? And the fact is that we don't actually encode a full description of the circuit inside of the circuit itself. In practice, we take it in as a public input somehow. And we take a commitment to a polynomial that encodes the circuit in some way, or several polynomials that encode the circuit, the verification key, for example, or whatever you want to call it. That gets brought in as a public input, and the verification routine works using that. So in fact, the goal is expressly that the circuit can reason about itself without it increasing monotonically. So it will stay the same size. We only have one circuit in this example.
But in your little arrow, you have, let's say, d-2 comes after d-1.
Mm-hmm.
This is just like conceptually what's happening. It's not like an actual thing in code where it's like constructs some circuit data structure from the previous one.
Right. So what I mean by the arrows is that there's some base proof on the right that was created, the first proof that was created, and we keep building proofs that take that. For example, the second proof we create would verify the base proof inside of the circuit, and you get a new proof. And we could keep doing this. And so what the arrow means is that it can attest to the correctness of a previous proof. So pi d can attest to the correctness of pi d-1, which attests to the correctness of pi d-2. And so inductively, we demonstrate every proof is correct up to the base case, but with only a single proof at the end, which is pi d.
So you don't have a circuit for each respective ICE D entry?
It's the same circuit. Each one's
It's
the same circuit.
Yes. Thank you.
The only thing that differs is which proof is being checked and what the public inputs that are brought in for that proof that's being checked inside the circuit, and also whatever other stuff you're doing in the computation step. I just kind of take that to be whatever's going on. It could be anything.
But it's not like
it doesn't. Sorry, carry on.
Wes. It's not like that circuit C somehow implicitly has a corresponding circuit for D-1 and D-2, right?
Right.
It's
just one
just
circuit.
one final.
Yeah.
Is it correct?
In general, it doesn't.
So it might be helpful for me to just like remove C there just to avoid maybe add VK as a verifying key or something like that. I don't know.
Maybe add commitment to C or something like that.
Yeah.
You said?
Yeah, that would be.
It doesn't have to be the same circuit. So as long as you can describe the circuit concisely, that's sufficient.
Is it at all correct to regard C as a function that takes itself or some other function as input?
It takes a encoding of itself as input.
Mm-hmm.
Yes. So the encoding of itself would be this verification key. So yeah. Okay, if that's clear with everyone, if there's anything confusing about that, let me know. I can try to clarify.
And you can actually have the verification key be variable. You can have a commitment to it in a different protocol or something.
Sure. Yeah.
It's very flexible.
So if we added multiple verification steps inside of the circuit, for example, so we're not just checking one previous proof, but we're checking two, then it sort of becomes a tree of proofs. And so you can do this sort of distributed computation stuff. This is called proof carrying data, or this is what that's a formalization of this idea. So the important thing to point out is that the recursive proof composition only works if the verification routine that you have to perform in the circuit, or you have to express as a circuit, is sublinear inside a sublinear size circuit or a sublinear time routine in the actual size of the circuit that it checks, which rules out immediately any verification routine that needs to have a full description of the circuit, because then it would never converge to a finite value, and you wouldn't be able to do anything but fixed step computation or composition. In order to do recursive proof composition, we need at some point the verification routine to be asymptotically sublinear in the size of the circuit that it checks. And as long as that's the case, then at some threshold, whatever it is, it will be possible to obtain recursive proof composition in either IVC or PCD, whatever it is you're trying to do. So unfortunately, that limits us in what snarks we can use, because there's only a few. There's pairing-based snarks, which use trusted setup, have constant size proofs and constant verification time, and that's really great. But of course, it requires pairings and trusted setups. Depending on what you're doing and what scenario you're in, it requires maybe large pairing-friendly curve cycles, and if you're trying to eke as much performance as you can get out of it. So it's a little tricky. You could, of course, use any snark that has sublinear time verifiers. For example, a Stark or Fractal, which came out last year as well. These are kind of heavy though, so it would be nice if there was a way to do recursive proof composition in a discrete log setting without a trusted setup and without having to rely on pairings and things like that. So that's what Halo is all about. So just as a sort of a little detour, I want to talk about polynomial interactive oracle proofs, or maybe the Marlin paper calls a similar concept algebraic holographic something. So the basic idea is that the protocol, it's a protocol for proving a proof of knowledge, or an argument of knowledge, where the prover sends, in practice, commitments to polynomials to the verifier, and the verifier responds with challenges, and the prover sends more commitments to different polynomials. Whatever it is, whatever the protocol really defines these polynomials is the important bit. But in the end, the verifier asks the prover to open all the commitments that they sent at various different points, depending on how the protocol is designed. And then the verifier uses those openings and any other information it needs to check that some identities hold. And if those identities hold, they're satisfied that the argument's correct. And of course, we can turn this kind of a protocol into, when these challenges are public coin challenges, we can transform this using Fiat-Shamir heuristic into non-interactive argument of knowledge. And if you have a pre-computation phase, for example, to encode the values of your circuit, all the wires and how everything comes together, a description of your circuit and anything else you need, you can also ask the prover to open those pre-computed values that were computed by the verifier and prover independently before the protocols ever were performed. And the prover can evaluate those, and the verifier doesn't need to evaluate those polynomials. Even if they know what they are, they don't need to evaluate them. They can just ask the prover to do it for them. And that's a useful trick that allows it's for pre-processing, which is an important aspect of things like Planck and some other protocols. So 2 important points on this. If our polynomial commitments are additively homomorphic, like group theoretic based polynomial commitments usually are, then we can perform a single opening proof, a single polynomial commitment opening, by opening a random linear combination of them in various ways. And I'm not going to go into detail about how that's done. It's not that important. There's a different talk, I think. There's a previous study session that talked about polynomial commitment schemes and stuff. So I'll kind of punt a lot of this off and kind of assume those that are listening know a thing or two about polynomial commitments. So the point I'm trying to make is that the cost is dominated. The cost of verifying a proof using a protocol that's a polynomial interactive oracle proof protocol is dominated mostly by that polynomial commitment scheme's opening verification routine, the opening of the polynomial commitment. So, for example, KZG10 or KT commitments, they use pairings and require trusted setup, but they have a constant time verifier and constant proof size. It's just a group element, which is really great. And commitments are just one group element as well. There's also these other polynomial commitments that we can build using a modification of the inner product argument that was presented by Boodle and Grott and all those other people. I forget all the other authors of that. And if you make a kind of a modification of this, and you can make it zero knowledge, and we actually describe it in detail in the Halo paper, a univariate polynomial commitment scheme based on the inner product argument. So that's in the Halo paper. It has a linear time verifier in the degree of the polynomial. So n is like the degree, and it has a logarithmic proof size. So that's really great, but it's not good enough for recursion because of the linear time verifier, which I'll get into in a second. So let me just do a kind of a quick pass over what this polynomial commitment scheme looks like. This one that doesn't require trusted setup, that's based on the inner product argument. So we have a vector G of group elements, and we have of length n. And if we want to commit to a polynomial, it's just a vector commitment scheme. You commit to the coefficients. That's it. So P is a commitment. We just do this multi-scalar multiplication here. This is an inner product notation, or my attempt at one. So yeah, it's just a simple vector commitment scheme. And when the prover wants to prove that their committed polynomial, when it's evaluated at some point x that the verifier has asked them to open it to, the prover claims it opens, P of x opens to V, and they want to demonstrate that the inner product of the coefficients with the different powers of this value x is equal to V, and that also the committed polynomial agrees with the coefficients that we use for that inner product. And so the inner product argument is sort of a general case of this this kind of thing. So we can make a very specific variant of it, and that's what we did in the Halo paper. It's not a very novel thing at all. It just like in bulletproofs, there's log 2 n of with respect to the degree of the polynomial, there's a logarithmic number of rounds. So the proof size is logarithmic. There's these elements here, which I'll see if I can get my cursor. L and R, which are sent in each round by the prover, and these challenges U1 through UK, which are chosen by the verifier as the protocol progresses. And so the verifier ends up checking this equation, which only requires a logarithmic amount of effort once you assume that the verifier has access to this value G. This value G, this group element, takes a linear amount of work to create. It's actually a linear size, linear time multiscalar multiplication that computes it. And it's computed as the inner product of this vector that has this kind of binary counting structure that emerges during the protocol. So it's defined, this vector S is defined by the challenges that are sampled by the verifier during the inner product argument protocol. And so it's just a vector commitment to all these weird, this weirdly structured set of values. So unfortunately, computing G requires linear time. It requires a linear time multiscalar multiplication. So we can't just put it, we can't just build a, we can't just use this as our polynomial commitment scheme and build a snark verifier inside of our circuit, because it's linear time and we won't be able to converge to a finite size, and we won't be able to get recursive proof composition, just like I was explaining earlier. So the value G, instead of computing it, we take advantage of the fact that the prover can supply it without actually computing it inside the circuit. The prover can supply what they claim is G, and then the circuit can proceed to perform the rest of the checks, which, like I said, this equation is logarithmic time in the circuit size. The circuit can proceed to just assume that G is correct and then perform all the rest of the checks. And then this value, this G, as well as the challenges that determine what G should be computed as, are taken as public inputs to the circuit. And as a result, the verifier of that circuit, or of that proof, is responsible for ensuring the G is correctly computed with respect to those challenges that come in as public inputs. So if we try to apply this to our recursion, or a recursive thing, or recursive context, we have this sort of verification routine. It's not a complete verification routine. Maybe I should call it verified partial, not instead of verified pass or fast. But essentially, it takes the old proof, and as public inputs, it takes the old G value that circuit wasn't capable of evaluating or checking itself, and then the prover, just like before, will witness what it claims to be the G value for the polynomial commitment scheme opening for the old proof. So now we have two instances of checking if one of these G values, if these G values are correct, with corresponding with the challenges that are sampled. So we can't just take two and then make those public inputs, because then the public inputs don't converge to a finite size, and we can't get recursive proof composition that way either. So we have to do something else. So we take advantage of the fact that the structure, this weird binary counting structure that emerges in this vector S that defines G, it allows us to actually reinterpret G as a commitment to a polynomial, just as if we committed to a polynomial, and not just any polynomial. It's one of high degree. It's a very complicated polynomial, but it has a succinct description. So we can evaluate it in logarithmic time at an arbitrary point. So as a result, what you could do is you could have the prover provide what it claims is to be G, and then open it up to a random point. And if the opening matches what our expected opening, then with high probability, the commitment is correct because of the degree bound of the polynomial commitment scheme. So that's exactly what we'll do. We'll, as part of the proof verification, we'll open the old G value at a random point, and then of course the verifier can compute what they expect that G value to open to. So we sort of integrate this opening, just like I described earlier, much earlier. We can throw as many polynomial commitments as we want into our proving system. At the end, it's just one polynomial commitment opening proof that needs to be performed because of the additive homomorphism of the group. So going back to where I was, yeah, so the prover will be asked to open that G old value at a random point. Verifier checks the opening, and as a result, there's this G new value that the prover has to witness, and we can take that G new value as a public input. And if the verifier of that proof checks that G new is correct, then we know that G old was correct, and inductively we know every proof in this tree of proofs was correct by induction. So kind of just to recap what I just said again, I guess, the proof being verified inside the circuit takes the old G value and all the challenges that were used to compute, that define it, as public inputs. The circuit checks that G old is correct by asking the prover to open it at a random point. And in doing so, as part of the proving system, whether it's Planck or Sonic or whatever you're doing, as part of that, you kind of shove G old into the opening, and you pick a point X and you open it. And if it agrees with what you'd expect it to open to, then you know with high probability it's okay. And what this effectively does is it transforms that old G old check into a new instance, G new, along with the new challenges for the new polynomial commitment opening proof. And then we take those challenges as public inputs, mirroring what happened above here. This is the exact same form. We've just transformed it into a new instance. And outside the circuit, the verifier of the recursive proof checks that the final G new value is correct. And if it is, then corresponding with the challenges. And if it is, then we know inductively that every G value inside of the recursion was correct. And so this is essentially what we refer to as nested amortization. We can rewrite this. Oh, sorry. I should allow for questions if anyone has a question.
Yeah, I had a question. So if you had multiple G old proofs that you wanted to verify, if you're doing the PCD scheme, how would that work here? You
the
just
same
combine
thing.
them using the additive homomorphism?
Yeah, exactly.
Okay.
So however many old G values you need to check that correspond with every proof, you just add it to your to the list of things that the prover's asked to open, and you also evaluate it using this this polynomial here that the arrow points to, and inside the circuit, which is logarithmic time. So yep, that's more or less what's going on. So what I was saying was that this is an instance of a broader concept that we refer to as nested amortization. So I can actually rewrite this slide a little bit, make it a little simpler. For the general theme of what's going on, there's the proof that we're verifying inside the circuit takes some public inputs, X and Y. And we want to make sure that X really is f of Y for some function f, whatever it is. In the case before, it was the multiscalar multiplication, but let's think abstract, so some f of Y. And we transform that into a new instance for some X prime and Y prime. We take those X prime and Y prime as public inputs, and then outside the circuit, we check that X prime is really f of Y prime. And we can keep doing this kind of collapsing procedure over and over and over throughout the recursion, all the way up until the end. And the final verifier outside the circuit can just check this value, and inductively we know that everything was correct. So this is what we refer to as nested amortization, but it's actually there's a better way of looking at what's going on here. It's something called an accumulation scheme. So the observation that was made earlier this year in a paper called Proof Carrying Data from Accumulation Schemes is that what we came up with in the Halo is just an example of a more general concept called an accumulation scheme, where we have a few different operations or a few different concepts. First, we have the accumulator. So for example, with the polynomial commitments, the discrete log-based polynomial commitment scheme, the accumulator is this G element along with those challenges. So the accumulator is brought in as a public input to the circuit. The accumulation step is the thing that happens inside the circuit that allows you to collapse multiple instances of these of the accumulator into one accumulator. So we just open G, the current value of the accumulator, using a polynomial commitment scheme. We get a fresh G and fresh challenges, and then we replace the current accumulator with those values. That's essentially what we're doing. And then at the end of the protocol, outside the circuit, we check that G is really actually a commitment to the correct polynomial using the challenges. And we call that party the decider. So the deciding algorithm is the expensive algorithm, but it's, in particular, it's the one that we don't put inside the circuit. And by doing so, this allows us to avoid the blow up in the size of the circuit that would result if we were to naively compute G inside of the circuit. Does anyone have any questions? Go up. Please feel free to interrupt anytime.
Also, there's you might want to check the chat real quick if you have a chance.
Oh,
there was a question from a few slides ago.
Chat.
Oh, hopefully you're able.
Where's
to
your
go
face?
back
I'm trying to hide my face because.
Just at the very bottom there, there's some questions.
Oh, I can just ask my question. I think you kind of answered it, Sean. I guess it was, so you use this term transform. And I guess it's unclear to me whether or not you're transforming it or if you're just taking, like, can you elaborate a little bit more on that?
Yeah.
It's not really transformation, right?
I don't know what the best word is for it, but what I'm doing is I'm trying to take multiple instances of something like this, where I want to see, is G old really correct with corresponding with this?
Mm-hmm.
And turn it into one instance of that same problem. So it's transform in that sense. It could also be amortize, or it could be, there might be a better word for it. But that's a,
so I like compress.
Compressing, that's great. Yeah, that's a good one.
I mean, right, but there, sorry, just to clarify, I mean, so G is a group element, and then these U's are coefficients to a polynomial. And so the transform is basically what? So you get like a group element and new coefficients, but they're new coefficients on the same polynomial, or?
So yeah, so G old is a group element that commits to a polynomial.
Right.
A univariate commitment to a polynomial defined by these coefficients.
Okay.
And
it sounds to me like that tuple of G and U's is itself a monoid or a semigroup or something like that. But it just has that structure. That's what that sounds like, the, you know, accumulating a bunch of instances of it into a new thing of the same type.
It's definitely a semigroup, yeah.
So, okay, so let me just, I like compresses, or like, I heard another one that was good. But that's a better instance of this. What we're doing is we're essentially saying, okay, so I have multiple of these G olds. I will have you prove to me that they're correct by using a polynomial commitment scheme to open them, which just takes a random linear combination of them and opens them at some point. I can compute very efficiently what it should open to. And if it does, then I know all those are correct. However, in order to check that proof, I need to compute another instance of this G old using these new challenges. So what I've done is I've taken multiple instances of this and compressed them or merged them or combined them into one check, which I can then expose as a public input to the circuit, sort of continually collapsing the process that needs to be performed.
My question is also on this slide. Oh, you just changed it.
Oh, it's on. Oh, you said it is on.
Yeah.
Okay, what's up?
Yeah. Says that it checks that J old is correct by asking the prover to open J old at a random point X. When it says the prover, you mean like the proving circuit or the actual proving?
The actual prover
entity. Okay. So it's
the
interactive.
Prover does it. Well, I mean, when I say ask, when it's not interactive in that it's not really interactive. It's just we're these circuits, and usually how this works is that the prover can supply values without actually having to compute them inside the circuit. The circuit assumes that the prover is being honest, and continues on with its checks. But it needs to know at some point, someone needs to know whether the prover was honest when it supplied that value. Because if the circuit didn't compute it, then the prover could be lying. So in that sense, it's not that it's interactive, it's that it's non-deterministic. So the circuit leverages the fact that the prover can compute this on its own outside of the circuit, allowing the circuit to be sublinear in size, and uses an argument that is efficient to compute inside the circuit to check to make sure that it's correct. And this process of compressing the checks continually throughout each cycle of recursion is exactly what allows the circuit to maintain the invariant that it is always, it converges to a finite size. So, and also that the public inputs don't grow in size. It's always merged together. Okay. So.
Oh, I have a question while we're here. So suppose you're using this for a blockchain application, say, and you want to upgrade the circuit, but your new circuit is larger. I think you can still do that, provided that so the cost of your proof will increase, but it'll only increase once when you increase the circuit size. Is that right?
Well, how would you do it though? Like you could, if you're going to change the circuit, you could just like take the recursive proof that you have at the boundary of the upgrade or the network upgrade or whatever you want to call it, and then just like give it to everyone and have them check it, and then use that.
That's a very good point.
State that it attests to it as for another, and then you're only paying an extra cost per upgrade. But yeah, I don't know.
That's a good point.
Yeah. Okay, cool. So I wanted to show other accumulation schemes, because this is one example of an accumulation scheme that allows us to actually get, ooh, whoa, okay, where are we?
Back a bit.
This is an example of an accumulation scheme that allows us, this is what's in Halo, this allows us to get, to use the discrete log-based polynomial commitment scheme to build, using Sonic or Plonk or whatever you want, to build a to build recursive proof composition or proof carrying data or whatever without needing a trusted setup. So that's really great. But there's a little bit more that you can do. So for example, if you were using KZG10 commitments, so you have some polynomial commitment P, you have an opening proof Q, you have an opening value V, so at some point Z that you evaluate your commitment, it opens to V, and you have some structured reference string, and this is just what KZG10 commitments are. If you need a refresher on this kind of stuff, feel free to, there's, like I said, there's other talks and other study club sessions that went into this sort of thing. And I think this equation's right. I kind of just eyeballed it. I'm not really 100% sure. But the verifier basically checks that this pairing equation is satisfied. Now, if there are two instances of a polynomial commitment scheme opening, kind of like what we have when we're doing this collapsing procedure, then what the verifier could do, so for example, I have this P and I have a P prime and Q prime. So there's two different openings and two different commitments. The verifier could just sample random alpha once they've obtained P and P prime and Q prime. And then we can take a random linear combination of the values that are on the left-hand side here, the G1 elements of the pairing, and the value on the other instance. So first instance, and then alpha times the second instance. And the same thing with the left-hand side of this side of the pairing equation check, Q and Q prime. So now we have this A and B, and the verifier can now check this pairing equation, and if it does this, it only performs two pairings, but it's able to check both of these polynomial commitment scheme openings. This is a standard batch verification technique that's used in Kate commitments. And this maps exactly to what we're doing in accumulation schemes. So we have an accumulator, which is two G1 elements. In our accumulation step, we have a random alpha that's sampled, and then we replace the accumulator with a random linear combination of the existing accumulator plus the check that we want to do. And then the decider outside of the recursion checks to see if this pairing equation check is satisfied. So you don't actually need to perform a pairing at all inside of the circuit, which is really helpful for avoiding needing to do really expensive circuits for like, if you're actually using pairing-based snarks with trusted setups for performance reasons or whatever you're using them for, this allows your circuit to be quite a bit smaller. And depending on what you're doing, it also allows you to maybe avoid having to do curve cycles where both curves are pairing friendly, because you can use this accumulation scheme for one side of a cycle for a curve that isn't pairing friendly, and use this one for one that is. And just as an example, this is something that
I think it's not so much the cost of verifying the pairing in the circuit, it's the complexity, because if you want to apply all of the optimizations, then it becomes very complex and hard to make sure you've done it all correctly.
That's a good point. However, this accumulation step thing is so much faster than a pairing. So like for example, I think the Aztec people, they're doing simulated arithmetic or whatever using lookup. I would much rather just do this, which is way more efficient than doing a gigantic pairing using simulated arithmetic. That's ridiculous. Yeah. So yeah, there's different trade-offs you can make. Oh, go ahead.
So Sean, what you're describing here is really a way of taking KZG proofs for k different polynomials and k different evaluation points and batch verifying them much more efficiently, right?
Right. So the batch verification technique that I'm describing in this is already very well known. This is something that was probably in the original paper.
I don't think so. No, I don't think this was well known.
It's aggregation rather than batch verification. So for batch verification, you still have the same size of input.
This is batch
well,
verification.
I'm just making an analogy to signatures. So an aggregate signature scheme, you can basically combine the signatures into one, which is what you're doing here, as opposed to having lots of signatures and just having a way to verify them more quickly. Usually only by a linear factor, as constant factor.
So I guess this was well known in the sense that we knew that you could batch verify pairing equations, but I don't think the application to KZG was well known.
Okay. Well, hopefully it's well known now then. It's great.
It's great actually. Actually, I think this has applications to other things too, like verifying shares in distributed key generation protocols, where you have a bunch of polynomials and you need to verify a bunch of shares on those polynomials.
Cool. Okay. Yeah. So. Cool.
It's one of these things where it's obvious after you see it, and then you're unsure whether it was actually a reinvention or not.
Great. Okay, so like I was saying, this batch verification technique maps to the accumulation scheme or the nested amortization stuff directly. So we can use it as another tool in our toolbox. And finally, to kind of wrap up for the day, I wanted to talk about another accumulation scheme that exists in, I don't know if it's fair to call it an accumulation scheme with respect to the actual accumulation scheme paper, because the formalisms might not match up and it might be a little bit orthogonal, but it works similarly. It's something that we put inside of the Halo paper. So in the Halo paper, we use Sonic on top of this polynomial commitment scheme, because we had done this. I think Plonk came out like days before we published Halo or posted Halo publicly. So it was too late for us to like mess around with that stuff. But and we would have gladly had there not been like 80 papers that came out in September. But so we used Sonic. We built Sonic on top of our commitment scheme, polynomial commitment scheme. And in Sonic, the verifier needs to compute this polynomial at some known points, x and y, this polynomial s, similar to what's done in bullet proofs. So this S polynomial is public. It describes the circuit. But what we do in Sonic is we have the verifier ask the prover to commit to that polynomial where y is realized but x is still unknown. So it commits using the univariate polynomial commitment scheme, commits to that, and then the verifier asks the prover to open S at x, and that gets them SXY, assuming the prover was honest when they committed to S. So if this is a necessary step that when you're checking a Sonic proof, in addition to the polynomial commitment scheme and checking the G thing, we also need to check that these S values are correct. And it turns out that there's this idea that stems from the Sonic paper, where if we have two instances, S1 and S2, where the prover claims that they were commitments to this S polynomial with different Y values, what we can do is we can collapse them into one instance. Collapse is another one of those words. Collapse, compress, whatever. We can collapse these two instances of this problem into one. Basically, the verifier samples a random value Z, and then the prover is asked to commit to the S polynomial with X realized as Z, but with Y unknown. So we can do that with a univariate polynomial commitment scheme. And then the prover opens S1 and S2 at Z, which should agree with the openings of C at Y1 and Y2. And if C is correct, then we know with high probability that S1 and S2 are correct. So to get things back into the original form that they were, the verifier samples another random Y3, and then asks the prover to commit to the S polynomial evaluated at with X unknown, but with Y evaluated at Y3. And then the prover opens S3 at Z to the same point that C opens at Y3. And if S3 is correct, then we know C was correct, which means we know S1 and S2 are correct. So now we have one instance S3. Is S3 indeed a commitment to this polynomial with Y3? Rather than two instances that we had before with S1 and S2. And so we can go back to our accumulation scheme slide and just right here, we can just write exactly what's happening. I meant to actually add some lines in between where the verifier samples stuff, which is just VHMIR or whatever, but I forgot to do that. But this accumulation step is exactly what I described on this this slide.
I think it probably does fit into the accumulation scheme formalism. I can't see why it wouldn't.
The reason why it might not is because the accumulation scheme is really okay. I'll have to look at the paper. It's certainly very similar, but there might be some specific thing with the accumulation schemes that talks about snarks and stuff like that, and I don't know. I have no idea if
So I think like it's interesting. Like you can think of it, say, instead of just giving you a bunch of univariates, I give you a bunch of univariates, but encoded in this way as different restrictions of the same bivariate, which is what you get. So can you, in this case, when I give it to you like this, accumulate / compress more efficiently than you do for general KZG univariates? And I think the answer is yes, right? I think the work of either the prover or or probably the verifier in this third case is a little smaller than in the second case.
What's the second case? You're talking about the second
regular
accumulation
KZG.
scheme.
I gave you a bunch of univariates compressed, and here you have a bunch of different restrictions of the bivariate.
Yeah. Yep.
So I just looked up the definition of an accumulation scheme, and they actually distinguish between the basic definition and an accumulation scheme for a snark. I think this does satisfy.
Oh, cool.
The
That's
basic
good.
Definition, which is
it'd be nice
just
to
for
actually.
a predicate.
So the accumulation scheme paper mentions this third one, not by describing it as an accumulation scheme, but by describing it as what they call a post-processing, which I find to be a really intuitive and interesting idea, because in Halo we don't since we do this third accumulation scheme, we don't actually have to perform any pre-processing. So we don't commit to polynomials that encode our circuit description, which is interesting from a theoretical perspective. It doesn't really pay off in terms, or it may not really pay off in terms of performance depending on what you're doing. But certainly does when you're using Sonic, because Sonic's very inefficient, but maybe with Plonk and other things, it's not really that helpful. I'm not sure. Cool.
Well, I mean, I think it is still, I don't know if anybody's really looked into it. Like say, yeah, you're in this, forget maybe recursion for simplicity, just you're doing a bunch of instances of the same circuit. I'm not sure we can rule out that like the Sonic bivariate thing can't be used to, you know, further improve Plonk/Marlin.
Yeah, so, something I was considering, I don't know, a few months ago, I was posting on the Plonk Telegram channel, was this idea of where this bivariate polynomial, S, actually encodes all the univariate polynomials that you need in Plonk to compute it for pre-processing. Like all the selector polynomial commitments and so on. And whenever you need to evaluate them or open them up at some points, then you can just use this technique at the same time and then bring it in as public inputs and do the collapsing thing over and over and over. And you don't actually have to perform pre-processing in Plonk either, which is interesting from a theoretical perspective, but I don't know.
Well, I mean, maybe it's more efficient. I don't know why you're calling it not doing just the pre-processing is this one S instead of a bunch of univariates. I don't know why you're calling it.
No, it's, so when I say pre-processing, I mean to say that this group element is computed before the protocol begins, right? But that's not the case when it comes to this S polynomial. These are computed as the protocol is ongoing and the verifier checks that they're correct at the end. Hence why I think the accumulation scheme paper calls it post-processing. So my suggestion, which I don't know how much of a theoretical or practical benefit it would be, probably none, but we allow all of the univariate polynomials that would otherwise have to come in as public inputs.
Oh, well, actually, so maybe it can decrease the verification key size, or no, but it is, I don't understand why not to call it pre-processing, right? You're just encoding the pre-processed polynomials in one bivariate instead of like 5 univariates, or I don't know why not to call it, I don't understand why it's not pre-processing.
I guess it's not pre-processing because we're not committing to a bivariate. We're committing to univariate using a specific Y that we ended up using.
Oh.
That's needed for that specific proof. So that this S commitment, S2, is not helpful for any other proof in the recursion, for example.
Oh, right. Oh, but
right, because the Ys have to be chosen by Fiat-Schauer, is that right?
Yeah.
Well, oh, okay, yeah, but
I don't know if that's enough of a distinction to matter, but yeah, there's one.
Yeah, but right, okay, but for that you need, okay, yeah, maybe this is, yeah, there's a lot there's a lot of sides here, yeah, but you can do that when you have a protocol where the verifier actually knows S and actually computes S at least once.
Right. Yeah, it'll have to evaluate S at the end or something. Or maybe fold it into some other. Oh, actually, I don't know. I think the prover you could combine this with pre-processing actually on the outside. You don't actually bring in the pre-processed elements on the inside of the recursion, but then you use the pre-processing on the outside to see if the commitments agree with each other or something like that. Maybe that's a way to do it. I'm not sure. Yeah, I'm just trying to suggest, I'm not really sure if this is helpful, but I'm just trying to suggest ways that maybe this style of an accumulation scheme could come in handy with Plonk or with recursion, maybe reducing verification key size or whatever it might be able to do. And I would really invite people to think about more accumulation schemes.
So I have a question about that. Can we think of post-quantum accumulation schemes? Because the proof carrying data from the accumulation scheme paper has a section on post-quantum security, and the same idea works, but obviously the the schemes here are not post-quantum secure because they're
Well,
a discrete log?
in some sense, like this third one doesn't have any. It's
just information theoretic. Yeah.
Right. It just depends on whatever the polynomial commitment scheme underlying it actually depends on cryptographically. So
that depends on the commitment scheme being additively homomorphic, does it?
No, it doesn't. Actually.
It doesn't. Okay. Right.
Where are the discrete log requirements in these two? So when you say that these should be post-quantum, like where are like the discrete log assumptions in?
So this top accumulation scheme is the discrete log-based, no trusted setup based on the inner product argument polynomial commitment scheme. It's an accumulation scheme for that polynomial commitment scheme. And the second one here is for the Kate commitments, which is pairing plus trusted setup. And this third one is agnostic to the underlying commitment scheme and its properties. So this third one might be helpful. Like, for example, in Fractal, I can imagine like if you're doing something with Fractal or whatever, I don't know, Starks, and you want to do, you don't really need it to be additively homomorphic, probably. You can probably do probabilistic stuff to achieve.
So can we
simulate
use
additive
this,
homomorphisms?
Can we use this to make Fractal more efficient? Because
right, I'm sure someone's
I think currently the recursive proofs mentioned in the Fractal paper, they just rely on the basic idea from BCTV 14.
Right.
So if you combine that with an accumulation scheme, how much does that help, or do we not know?
Yeah, I don't know that much about fractals, so I have no idea. But I would guess that someone's thinking about that. Probably Alessandro and his students, if anyone. But yes. Okay, so that's all I had in terms of slides. I'm not a good teacher, so I was probably confusing and probably skimmed over things. No, I'm not. But I tried. So here's some reading material, the Halo paper, the accumulation schemes paper. I tossed in Supersonic and Marlin because they have formalizations for things that are like polynomial ILPs. I don't really know that much about those formalizations. Well, I know enough to be able to talk about them, but I don't really care about formalizations like that. But if you're interested, check it out. And then there's the fractal paper that we were referring to, in case you aren't aware of that. But besides that, I would love to answer any questions anyone has and go through the slides or whatever. But I don't have any more material outside of that. But thank you for everyone for bearing with me and attending. Thanks.
Thank you.
Cool. I'll add those links. I'm going to be putting this on YouTube, so I can actually put the links to those papers as well if anyone wants to.
Okay, cool. Yeah, I could send you these slides. I'll post these slides so anyone can check it out.
That would be great. Yeah, that's good. Mm-hmm. Cool.
Can I ask, just next week, Dara is going to be giving a...
Yes.
Sort of, is it going to be like more like a follow-up or like a different topic? Like
it's kind of half and half. So part of it is how to optimize Halo. And part of it is constructing the elliptic curves. So for the elliptic curve part, I actually talk about a more general case where you're constructing graphs of elliptic curves. So obviously one case of that is a 2-cycle. I explain why you need to use curves that have complex multiplication to get cycles. But I also go into sort of how we use an endomorphism on the curves to optimize some of the operations in Halo, things like that.
Awesome. Thanks, Dara, and thanks, Sean, for the awesome presentation.
Thank you for your time.
Hey, so I'd like to make Sean talk some more, but I guess how much time do you want to take beyond here?
I'm happy spending like another half hour or whatever answering anyone's questions.
I think we're chill.
Yeah.
Okay, excellent. Okay, yeah, I think I'd like to build a better intuition on how you get kind of the new G from the old G. I mean, I think you had an example way at the beginning of the talk that you kind of skimmed through there. But I feel like if I had a more concrete example, that would kind of solidify the abstract concept for me a little better.
So it might help to explain where this structure comes from.
I could do that.
I guess
would hope that I
that's,
could get away with not doing that.
Right. I guess
Okay.
that's already in the bulletproof paper. So.
Yeah, I recognize that, all possible combinations of the U's with their inverses. I recognize that from the bulletproof paper. I guess I kind of missed how you go from one step to the next, really, that's all.
Okay, so in this adaptation of the bulletproof style polynomial commitment scheme, like I was saying before, commitments to polynomials are just commitments to the coefficients, vector commitments to the coefficients. So if our coefficient, if our polynomial is defined like this, then this is our commitment to that polynomial. Easy peasy. Now, it turns out that, and I can explain why, but hopefully I don't need to, but it turns out that in order to actually check this equation, the verifier needs to compute this group element that's computed as this with S, defined as this, and you've seen this in the bulletproofs paper. Well, this S vector can just be interpreted as coefficients of a polynomial, right? This G value is the same thing as a commitment to a polynomial, just like what we did before here. It's the same thing, but just with S as the coefficients. And it turns out, and again, I can go into detail why, that this G value can be interpreted as a commitment to a polynomial that has this succinct representation. It takes only a logarithmic number of steps in order for me to evaluate it at a random point. So let's say I have two of these G's, and they're defined by different S vectors because they were created with different challenges or whatever. And I wanted to I wanted the prover to assist me in determining whether those two are correct. So what I can do is I can take a random linear combination of the two G's and then open it at a random point. And I can compute what I expect the evaluation of it is. Now, if either of those G's weren't correct, they weren't commitments to their respective S vectors, then with very high probability, given a large enough field, the opening argument of the new linear combination of the commitments would not open to the correct, either the argument would fail or would open to a different point or to a different value with very high probability. So we know with high probability, or I should say it the other way around, but with if it opens to the correct point, then with high probability, we know the original two G values were correct. And of course, opening a linear combination of the original G values using the polynomial commitment scheme necessarily requires us to go back to this equation, but this time with a new vector S, we have to compute this G. And that's sort of what's happening in the accumulation scheme. We're collapsing the G in each step, the G value in each step with a new fresh instance of G in that sense. Does that help, or is there something missing in that description?
On slide 19.
Yeah.
Can you just explain why that the second bullet point is true?
Why? The reason why it's true is so it's just the structure of the S vector that makes this happen. So basically, it here. Actually, I kind of prepared for this a little bit. I have a little pad here. Let's see if this works.
Yay, we get to use it.
Yeah. So I don't know. I don't really know what I'm doing here. Let's take an example of like k is equal to 2. So we have U1 inverse and U2 inverse times G. I guess I'll just do a one index plus, I think this is U1, U2 inverse, G2. Thanks for bearing with me. So this is the structure of this G element, depending on the challenges U1 and U2. Now, we can rewrite this as a polynomial. So if we rewrote this as a polynomial, we do like U1 inverse. I can actually do that without having to rewrite it. If we rewrite this as a polynomial commitment, or sorry, if we rewrite this as the polynomial that it represents, as this commitment represents, let's see if I can get rid of these. Okay, perfect. I'm having fun here. What we're going to end up seeing is this sort of like self-reflection, or I don't know what you'd want to call it. So what this ended up being is like U inverse plus, or sorry, U1 inverse plus U1x, which is sort of, if you pretended like there was no second challenge. Am I explaining this right? But I haven't explained this before, so I don't know if it's helpful. But yeah, okay. So if we look at like the equation, okay, it's the other way around. So that might be actually wrong. I don't know. It could be, yeah, that might be backwards or something in the paper, but yeah, so it just ends up being that this describes it. I could like sit here and fumble around until I figure out the best way to describe it, but I'd probably just waste everyone's time. But yeah, if you actually like, if you looked at it and you tried to figure out like, how do I describe this? How do I efficiently, like, for example, compute this multiscalar multiplication? If all you could do is multiply by challenges, you'd realize that you could do it like, you realize that you could like break it apart into smaller and smaller pieces until the polynomial just.
Oh right, you just break it into half multiple times.
Gus,
Okay.
did that answer your question, or did you have more to that question?
I don't think I have much more. I guess maybe I would just close with like this little bit of feedback. Like, it'd be really nice to have a concrete example that can kind of really drive home the wow factor of like, wow, you've compressed all of these linear time checks that the verifier has to do into a single one at the end. And I feel like right now I'm kind of like missing that punch. I mean, I think there was a lot on the abstract.
Oh, okay.
And I guess, yeah.
Yeah, I sort of.
But that's like, I'm not asking you to do anything more. That's not a question. That's more just like a comment. Of course, if you feel like following up, then I'm happy to listen. So thank you.
Yeah, like I was saying when I first started the talk, I really suck at visualizations. So what I would really like to do, if I could, is to take like this diagram here and start putting G's and stuff in it, so that you go, oh, I see what's going on. But of course, I'm seriously, I'm gonna have to need to hire someone to make graphics for me, because I just can't. This is the best I can do. Sorry, I can't get you the wow factor, but yeah.
All good, thanks a lot.
Yep.
I appreciate it.
Yeah, no problem.
Any other questions in the group? There's still like quite a few people here. There's also a little bit of chatter in the notes if you want to check.
I keep forgetting to look at the chat.
But while anybody else is thinking.
Cool. Oh, I don't really have a strong opinion. Like if you,
we should actually say for the people watching on YouTube what you're talking about.
Okay, sure, yeah. So the question is like, I'd be interested to see a mini debate with Ariel and Zach if you guys are up to it. So the question is the Halo or Aztec style recursion, which one's better? I think it depends on what you're doing. Like clearly Ethereum, the way Ethereum is today, it cannot handle a gigantic multiscalar multiplication to check a recursive proof. It can handle a pairing, and so that's kind of why you would probably want to do Aztec style recursion, which is basically just this second accumulation scheme. As far as I know, plus like lookup or something. So that's
Zach is actually on the call. I don't know if he's.
Yeah. The interesting question
wait, can we just hear from Zach real quick? Because I just.
To be honest, actually, I wouldn't mind hearing from Dara first.
Okay, go ahead.
So to me, the interesting question is whether it's better to do the pairing basically in every other step. So say you have a half pairing cycle. Is it better to do the pairing every other step, or is it better to just use the discrete log scheme and then do the pairing at the end? So the advantage of doing the pairing at the end is that you end up with a shark. So you're only relying on the pairing to get O1 verification. And if you don't need that, you can still do the decision on the accumulation scheme.
Yeah, I think I might not have fully understood the question. It depends on whether you care about the minus process setup, because if you don't, then just the one with the lower recursion bound matters. I'm happy to talk about it. I'm not sure there's going to be much of a debate here, because I think like basically they just occupy very different places in the trade-off space. For the lowest recursion bound possible, it's pretty clear that Halo is going to give you the best, the lowest recursion bound by quite a wide margin. The reason why we're using is what Sean said. The reason why we're using kind of just like brute force recursion and clickups is twofold. One of them is the absolute need for a fully succinct verifier. The other one is it's quite Ethereum specific, but we're very restricted in the types of elliptic curves that we can that we can support. Specifically, there are two. There's the BN254 and there's BLS12381. And so if you want to support recursion on both curves, then it's difficult. You can't directly use a half pairing friendly cycle on BLS12381 because the fields, the prime field size and the group orders don't line up. And there's also the additional complication that the prime field order of the BLS curve, it's not like, it doesn't have a high two-edicity. So if that was the native modulus of your field arithmetic, then performing the polynomial arithmetic required to make a proof would be challenging.
So, sorry, say that again. I think I missed something that you said there.
So it's just that. So imagine if you, I guess it's actually more academic, because there's no way that it's not possible to create kind of a cycle where you have a curve where the group order is equal to the prime field characteristic of the BLS12381 curve. But even if you could, creating proofs over that curve would be very, very challenging, because you wouldn't be able to use base 2 FFTs because of the actual value that prime number would take.
Right. I mean, the half pairing cycles, you can get both curves to have high two-edicity, but obviously Ethereum doesn't support that.
Yeah, and that's kind of the crux. I mean, if if we didn't mind a linear time verifier, even because the recursion amount is quite low, like maybe calling linear time isn't particularly fair, because if you can take a complex circuit and just break it down into multiple recursive parts that have a smaller size. But even in that context, you can't do very many exponentiations in a smart contract.
Yeah. I mean, what is the prospect of getting Ethereum to support more curves?
I can't speak for the Ethereum Foundation. I can speak I can just give my personal thoughts on it though, which is that it's going to be it's not impossible, but it's challenging because I mean we have to remember that the actual individuals that will be required to actually maintain support new curves are the implementers of the Ethereum nodes, Geth parity, and others, and they don't have in-house cryptographic expertise. So the barrier to adopting new curves is extremely high, because not only do you have to supply the libraries that implement the curve on a variety of languages, but they have to be kind of industry proven, as in widely used elsewhere in industry, so that they can be confident that there aren't any bugs that they'll be called on to fix.
I mean, I guess at ECC we kind of think nothing of generating new curves, which is a bit unusual. Yeah, I can see why that doesn't work for other people.
To give more color maybe on why BLS 12381 actually did get into Ethereum now, is that Ethereum 2.0 uses BLS 12381, and you want to verify deposits that are related to ETH2 on ETH1. So that helped a lot to push 381 into ETH1. And there was a previous effort by the Meta Labs people where they tried to get an EAP that would support any curves up to a certain size of many different kinds, like BLS curves and MNT curves and so on. And that one eventually did not get enough buy-in from the core devs. I mean, for good reasons, because like Zach said, they don't have this desire and expertise to maintain such a huge cryptographic library, but they did agree to insert this EAP for a specific curve after some work.
Yeah, I think that the general IP, I can't remember its number, but I have looked at it. There was a limit on the curve size, which would exclude half pairing cycles, because you want a half pairing cycle to be about 384 bits. I think it was limited to 256 or something.
So I think you were looking at an older one. There was one that supported even bigger ones, like up to the MNT curves that are used in Coda.
That would have worked then.
Yeah.
I'm actually quite keen on the half pairing cycles, because you don't have to rely on the pairing for the accumulation step, but it's useful to have it at the end.
So yeah, I have a question on that actually, because this might just be by a lack of knowledge, but even if you have a half pairing friendly cycle, because of the non-pairing friendly curve, you still have a linear time computation that somebody needs to do, either in the pairing friendly circuit or in the verifier algorithm. But it seems like, I mean, if you can afford the linear time verifier, then I mean the problem with the half pairing friendly cycle is surely it'll be quite a bit less efficient, because it's pairing friendly. You have to take into account the number of fields you've attacked and use a bigger curve, and then that curve's order has to also be reflected in the non-pairing friendly curve, so that you can have a cycle. So instead of being able to use a 256-bit curve, you have to use a 384-bit curve.
Yep.
Do you think that's? I'm curious. What is zkStudyClub using?
I don't know yet. It depends very much on how fast the Plonk-based Halos verifier turns out, and we don't know yet because we haven't.
So obviously it's a little different with Ethereum and with us because we can do batch verification between transactions. So whenever we have like a transaction that we need to do this linear time verifier, we can combine it obviously with all the other checks. So there, if Ethereum supported those kinds of batch verification things across transactions, maybe it wouldn't even need to be consensus critical change. It might just need to be a code architecture change to support that kind of thing. But I think that would make the multi-scalar multiplications of the kind that you have to do for these discrete log-based accumulation schemes a little more attractive in the Ethereum context. Of course, the circuit that's on the side that's discrete log-based doesn't have to grow. It just has to be able to, well, it doesn't have to grow very quickly anyway. It just has to be able to get you around the cycle. So that seems like it seems like in some contexts it should be reasonable to expect the performance to be good enough.
Yeah, I think this is,
assuming Ethereum were to support those kinds of batching things.
This is an underappreciated point, and I hadn't actually appreciated it until Sean pointed it out. With Halo, you effectively have two proving systems that are interleaved, but they don't have to be the same size circuit. So you could, for example, if you need a large circuit, you just put that on one of the curves, and the other curve is the circuit is only logarithmic in the size of the large circuit. So you can end up with sort of nice asymptotics. Yeah.
I have a question about the aggregation. Would it be fair to say that this could be implemented at the smart contract layer where you have some sort of aggregator helper smart contract, and then you kind of split the gas fees somehow?
I don't know specifically how Ethereum works with that kind of thing, but it seems in principle like there's some way to do that, because obviously there's batch verification which the node can do, but then there's also this coordinated aggregation that can be performed. The accumulation scheme can be used across transactions. So as long as someone's willing to pay the computational cost, they can get multiple transactions to share the same multi-scalar multiplication, if that mattered. But
I mean, it's easy to do batch verification across all transactions in a block. It's slightly more difficult in the mempool because you have to deal with denial of service attacks. If an attacker could submit a bunch of transactions, and you can't necessarily distinguish which ones were submitted by the attacker and which by honest parties. So you end up having to verify all of them individually in the worst case.
Hey, here's a weird idea. What if you had what if your protocol that uses like Halo or whatever on top of Ethereum, the smart contract assumes that the G that's provided is correct, and there's like a bounty on, and whenever you like update the contract state or whatever, there's some, not a bounty, like a bond or whatever you want to call it, where you lose your bond if you supplied a G that was wrong, and then the smart contract could be used to check it.
So similar to optimistic rollup, that kind of thing?
Yeah. Yeah, pretty much, yeah. Optimistic rollup plus recursion.
I mean, it doesn't even have to be optimistic. Like you could off-chain, like aggregate a bunch of proofs and then, well, collect a bunch of proofs, do the aggregation, and then submit them on-chain all at the same time as one batch.
Right.
I think even with aggregation, though, I mean, it would be challenging without some protocol support, because like you'll slam into the block gas limit by doing, I think, like 1,000 scalar multiplications right now. So even for like a recursion bound of say 2 to the 10,000. I mean that's munching through 10 blocks of gas. I mean I guess there's always going to be like there's going to be a some bound by which where that's going to be where you can amortize that enough to be practical.
But Zach, couldn't you like divide this computation into, let's say, 10 blocks, like 10 transactions, if you really wanted to for application?
Yeah, it's just crazy expensive, so you have to amortize a lot to justify it.
Yeah, sure. Yeah.
I mean, as I understand, the current Ethereum multi-X doesn't do like Pippinger or fancy experimentation.
There isn't multi-X.
Yeah, but it does the gas price take into account the fact that you can heavily optimize it with a cleverer algorithm?
No, not at all. You could implement like a straight up Halo verifier, and it would be like probably fast enough to be practical as part of the Ethereum protocol. It's just I guess it goes back to the question of actually getting those kinds of upgrades into Ethereum clients. If someone turns up with like a crazy optimized Intel assembly of implementation of Pippinger and hands it to the Get Parity team, they're going to take one look at it and go, I can't maintain this.
So they would probably be right.
And I think like it has wider implications, because if it's only Intel optimized, then it means that every other platform would suffer. So maybe that's not acceptable.
So there is a team, the supranational team, that's building kind of like assembly optimized implementations of these things, and they're doing formal verification. I guess when you have the two combined, then it might be.
Maybe.
Yeah, but that would exclude all the nodes that are running on, I don't know, different machines. I'm not sure if that's acceptable.
No, so you're right. So right now they're focusing on x86, but ARM is in the roadmap, and then once sufficient platforms, then that could be acceptable.
Yeah, sure. So if like all platforms has efficient enough implementations, yeah, that could make sense. I agree. Cool.
Yeah, that's really interesting. But yeah, it would take that kind of effort and formal verification to get it over the line.
Hey, so we're at the half-hour mark. I think at least for the recording, I'm going to wrap it up here. But we can actually keep speaking afterwards. But I want to say a big thank you to Sean for doing the presentation. And thanks to everybody who kind of joined in and helped to refine and work with this presentation. Thanks, Sean. I don't know if you're still here.
Thank you.
I'm still here.
Thank you.
Yeah.
Cool.
Thanks.
All right.
My pleasure.
Okay.